change topic a bit, and I'm going to talk about automatic generation of test cases for object-oriented imperative languages or programs, Java-like programs. Okay, this is of course joint work with a number of people. And let me introduce a bit the problem. So the problem is, we all know that software testing accounts for a high percentage of the cost of software development, and so it's important, and there are actually many levels at which you can try to automate things. So one of such levels is the generation of unit tests. Okay, so we focus on this. We want to automatically generate unit tests. And then let us think about what a unit test looks like. So basically, you have like two main steps. So firstly, you have to create the data with which you are going to run the unit under test, the method or procedure, or whatever, and then you have to check whether the result is what you expect. So the second part is so-called the test oracle, and this is usually done by, the tester has to write the specification, and then you look at the post condition. You have to check whether the post condition is met. And let us focus on the first part, which is the generation of the test data. So this can be generating like primitive types, or it can also be generating complex relationships among objects. You have to create a whole input state so that you can run your method. Okay, so this is the problem, and there are different ways of approaching it. There are different ways of solving. So the first attempt has always been to, let us do random generation of inputs, and then, you probably, in this way it is very difficult to achieve a good coverage of the code. So there are other ways in which you can use different sources of information. So you can either use the specification and you do black box, and then you can also use the source of the program, in which case you are doing glass box test case generation. Okay, and then we focus on this, and once you want to use the source, then you can do two different things. So you can either run the program with different values, and then you can check the values accordingly, so that at the end you get what you expect, or you can do that statically without running the program. And for this, the standard approach is to do symbolic execution. Okay, so we focus on this. This is the way we will try to solve this problem. So we want to do symbolic execution of the program, and this basically consists in running the program, but without concrete data. You start with symbolic values or constraint variables, and then it will happen that at any branching instruction where you do not have, or you have unknown data, then you have to consider the different branches. And then at the end, it's like you are generating somehow the whole execution tree, and then associated with each branch, you get a set of conditions or constraints. So that if you solve these constraints, then you are doing test case generation. You are getting an input that is guaranteed that if you run the program with this input, you will go through this branch, the execution tree. Okay, so this is the approach that we are interested in now. And this is what we have been doing for a couple of years. So we want to do automatic test data generation by symbolic execution, considering object-oriented programs, and in particular we have been targeting Java, actually Java Python. But we have always been trying to be language independent as possible, so that we can reuse our techniques. And we are developing a tool which is called PET, which I will show it later, but basically it is integrated in the Eclipse environment. So you are programming, you are the tester, then you can, you have your methods, and then you can select the methods for which you want to get automatically test cases or unit tests. And then automatically you get unit tests written in JUnit, or you can either, you can also observe the tests by looking them in a graphical way. So we will see this later. And those are, some aims that we have always tried to have in mind when designing our techniques. So, unlike other approaches where you generate millions of test cases and then you check them against these specifications, so we try to do a different thing, which is to obtain high degree of coverage with the less number of test cases possible. So, in other words, we want to obtain high quality test cases, so that a tester can even understand them and can even edit them. Okay, and this would be also interesting not only for doing testing, but also for doing program comprehension, which is a technique of, you can do in reverse engineering. So you imagine you have a method, a bytecode method, for instance, and you want to know what the program computes. Then you can generate a set of test cases, and then by observing the behavior or the input-output behavior of this program with this set of test cases, then you can do some program comprehension or reverse engineering. Also, we want to be complete with respect to the coverage criterion, and we want to be flexible with respect to the coverage criterion. Okay, and this is the approach that we have proposed 2 years ago, and we have been working hard on extending and improving it in many different ways. So basically, we have 3 steps. The first one, we transform whatever program, in our case it is Java, but this is generic in some sense. So you have some imperative object-oriented language here, and then you compile it to a constraint logic program, right? And then we formulate the engine of the test data generation in constraint logic programming, and then we get a set of test cases. This is the core of the scheme, and then you get the test cases in some CLP format, and now you can basically do 2 things. So you can either have a viewer so that you get a graphical representation, or you can try to generate AL code, and then you get unit tests. In the particular case of Java, that would be JUnit tests. Okay, so this is the basic architecture, and well, we have these strengths. So this is simple. Compared to other approaches where you have to develop from scratch a symbolic virtual machine for a particular language. So we here, since we are relying on constraint logic programming, developing it here, as we will see, it is much easier or simpler. Then this is language independent. This is the core of the architecture. So in this sense, we have genericity with respect to the input language, provided that you can compile it to CLP. And well, it is also very flexible. The different features that we have had to integrate, we have always seen that it is somehow, it is more or less easy to do. So it is quite flexible, especially when you have to try to plug in new or different coverage criteria. Okay, and so the question is why constraint logic programming? Okay, we like it. This is one reason, of course. But so the first one is the following. So the translation of object-oriented programs to CLP has been subject of active research and of our research, actually. So we have been working, this was the work of my PhD thesis, on the translation, applying the first Kitamura projection from bytecode programs to CLP programs. Okay? So the first Kitamura projection basically says that you can compile, or in this case we say decompile. So you can transform a program written in some source language into another language, object language, by doing a partial evaluation of an interpreter of the source language written in the object language. Okay? So what we did is we had a partial evaluator of constraint logic programs. Then we had to write a bytecode interpreter written in CLP, and then the technique says that you can then compile from bytecode to CLP automatically. Of course, that required a lot of work, but we did it. And then we wanted to take advantage of having this transformation. And the second reason is that in CLP, symbolic execution is somehow natively handled. So you already have backtracking, and you already have constraint manipulation and so on. So in principle, it is quite, it is a very good starting point if you want to do symbolic execution. This is what we thought. And actually, I would like to show you an example later, in 1 minute. So that will be the source of the example. This is a very simple method. It just computes a to the power of n, and we just check some conditions, okay? And in which case we throw this exception. So we are not allowing negative exponents. We are not allowing 0 to the power of 0. And then otherwise we have the typical loop here. And then, well, I don't have a lot of time to go into the details, but basically we start from the bytecode. So that would be the control flow graph of the bytecode. And then, well, let us just observe the arrows here. So we just check the condition. If it is less than 0, we throw the exception. Otherwise, we go here, and then now we check another condition. Then if both exponent and arguments are 0, then we throw the exception, and otherwise we go to the loop. So the loop is these 3 blocks here, it's represented by these 3 blocks. So this is the entry, we check the condition, and if it is, if n is less than or equal than 0, then we just end, and otherwise we go into the loop body. Okay, so, and here at the bottom I will show basically, this is, well, it's a bit simplified version of the constraint logic program that we get automatically. So basically you can see the correspondence between the rules and the blocks in this control flow graph. So this is the beginning just, this is 2 rules corresponding to these 2 flows. So if n is greater or equal than 0, then we go to another rule, I will show it now, and otherwise we throw the exception. And then that will be checking the second condition, that will be checking the third condition, and then if we go to the loop init, then this is how we are representing in CLP the loop. Okay, you can see that we are using now recursion, of course. So we have the base case, and then we have the recursive case where n is greater than 0. Then we do these operations, and then we do the recursive call. Okay, so this program is semantically equivalent to the bytecode to the initial source bytecode program. And now I will show you that actually once you have this program, you can do, or you can think about doing symbolic execution quite easily. So I have the program here, so that this is the same program we have just seen. Okay, so the program is here, and then we can take this. So this is loaded in Prolog, and so we can run it. For instance, this is not very interesting. I'm running it with equal values, but just to see so that we get things we expect. And also I have to talk about the arguments. So we have basically 2 sets of arguments. We have the input arguments, and then we have the output arguments. So in the input, we have on one hand the input parameters. So we have the exponent, the base, and the exponent. And then, since we can have references here, then we need to have the objects that those references are pointing to. So we need those objects, and also those objects can have fields pointing to other objects. So we need a set of objects. In other words, we need the input heap. And in the output, we get the original value, and we also get the output heap. And additionally we get a flag to indicate whether the execution goes normally or it ends with an encoded exception. So in this case, we get that the output heap is the same as the input one because no objects are being built, and then we get the exception flag OK. So we can also check, for example, putting here a negative value, in which case we get an exception. So this is the exception flag, and now we see that the output heap contains whatever it was in the input heap before the execution of this, plus this new object, which is an arithmetic exception. Okay, so this is complete execution. Not very interesting, but the interesting thing is that now we can put here variables. So this is what we mean by doing symbolic execution. And then we get constraints for all possible executions that the program can generate. Actually, this is an infinite tree. So we can continue getting things, right? And we can actually do it better. So we can try to generate test cases by setting a domain for the input variables. Okay, so we say that they are between -10 and 10. We do the call, and then we ask CLP, or we ask the solver to obtain particular values, okay, solving the constraints. So we get the following. So we get, for instance, those are different test cases. So we get that you can do -10 to the power of 0, and then you get 1. Then you then you can do this thing, -10 to the power of 1, and then you get -10, and it keeps remain the same, and so on. Right? Then what happens here is that we are now in a loop. So we are getting like solutions. Those are solutions corresponding to different paths of execution. That is the idea. But in this case, we are just obtaining the solutions in one path, which is like, I mean, not one path, but the same part of the tree in which you are in the loop. And then you can go one iteration more, and then you get another test case. So the problem is, basically the following. So we are generating a symbolic execution tree which looks as follows. So we have successful branches, we have unfeasible branches, and then we also have infinite branches. So we are now in this infinite branch, getting more solutions. But so in this way we cannot see all this part of the tree. So what we have to do is, in order to do test data generation, we want to do symbolic execution plus the constraint solving plus termination criteria. So we need to somehow stop this derivation tree, and then it can be done this way, right? And then we ensure finiteness of the process, and then we have a coverage criteria, basically. So in this case, I mean, doing a straight line here means that we are stopping derivations at a certain number of derivation steps. So we just allow a number of derivation steps and we stop. And there is a better way to do this, more intelligent way to do this, which is let us control the number of iterations on loops or the number of recursive calls. Okay, this is much more intelligent. So in this case, you are somehow allowing some derivations to proceed further, while others are stopped earlier. I mean, this one might correspond to a case where you do 2 recursive calls, for instance, and it can happen that you go very deep in the tree because you are not doing recursive calls in this branch. Okay, so this is the idea. And actually, I mean, to show you how simple it is to start. I mean, later you will have to face lots of problems, but in principle, I mean, you can do the following. So I wrote here a meta-interpreter in Prolog that do this. I mean, it just stops derivation. So it is like 10 lines of code, and then we just, I mean, this predicate will stop derivations. If it fails, then we stop derivations. Okay, so we can do the same as before. So now I can do this call. I'm doing a find all of the same goal that I did before, but now with the solve predicate, with the meta-interpreter, right? So I'm stopping derivations. I'm allowing here just one iterations on loops, okay? And then this is the way we can get test cases. So those are test cases. So we get that -10 to the power of 0 is 1, and then the exception flag is okay. We get this other test case, another one. We get 5 test cases. For instance, the last one is that 0 to the power of 0 with wrong exception. Okay, so this is the main idea. Any question? Is clear? Okay. Right, so as I said before, this is a good starting point, but there are lots of things that we have to take into consideration. So the first one I already showed how to solve it. So we need to ensure the finiteness of the process. Then whenever, I mean, in this example we just have integer numbers in the input, but when you have objects, then things can become much more complex. So you need to handle the creation of heap-allocated data, and then you consider object-oriented features, and you have inheritance, virtual locations, and aliasing. Those are problems that have to be addressed. I will go into some details later. Then also compositionality is a very important thing here, because I mean scalability of symbolic execution is a problem. So you need to find ways of alleviating scalability, and one is to do some kind of compositional symbolic execution. Okay, I will explain this later a bit. Then, well, also it is important to put the ideas in practice. So we have been developing this tool, but I will do a demonstration later. And then there is an interesting new topic that we are now studying, which is let us try to find test cases that reach to a specific program points, or that leads the program to a specific states that can be very high memory consumption, or a raising of some exception, these kind of things. So we call this guided test generation. I mean, we try to guide the symbolic execution towards some interesting paths. Okay, so this is basically the outline of the rest of the talk. So the first one, you will show it, and then let us go to the second thing. Okay, so this is a very simple example where I have, in the input I have an object of class A, and then this is the simplest thing that you can think of to solve this problem. So you have field F, and if it is less than 0, we do something, and otherwise we return the field G. Okay, so in this case, we have, if we are a tester, then what we have to do, if we want to achieve full branch coverage, so suppose we want to generate a set of test cases to cover all my code, all the branches of the code. So I need to create, before running the method, I need to create an object of type A, and then in one test case I will have to have the field F negative, and in the other I will have to have a positive or 0 argument. Okay, so basically, let us get familiar with this syntax. So this is the input argument, this is a reference X, and then that will be the input heap. Basically, this is a list of pairs, and then I have for reference X, I have an object of type A, and the fields are field F-1 and field FG1. So this is one test case, this will go through the if, and then we get this output. So that will be the set of test cases that I want to get. Okay? Then that will be a second one, in this case where I have a positive F, and then I'm going through not through the if, but continue it directly. And then I have a third test case, which is, okay, what happens when the input is null? Okay, in that case, then I will throw an exception, because I'm attempting here to access the F field. Okay, and then in that case I will get this. Okay, so how to do this? Well, interestingly, we have been able to do this just by writing in the appropriate way the built-ins that have to handle the heap operations. And when I say in the appropriate way, it means that instead of writing them in 3 lines, we write them in 4 lines. To be very careful on what you do, but if you do it fine, these built-ins that are in the program, get field and set field, then you can achieve this. Okay, so again I have here the CLP program. Then if I have a valid reference, then we get the field F, and then we check the condition. If it is less than 0, we set the field and we continue, and otherwise we just continue. And if I have a null reference, then I create a new object and I return this exception flag. Okay, so this is our program, and let us see how the symbolic execution proceeds. So I run this goal with input variables, and now what happens is that I reach to this point. So what I have to do is that I have to write this built-in get field in such a way that it can deal with partially instantiated heaps. In particular, in this case, I have a variable, so it has to work with an input variable. And what it does is that using logic programming, it just instantiates this variable with the contents that the heap must have in order to go, or in order the program to go through this path. So we do this instantiation. Okay, so we need to have an object pointed to by X in which the field F is F, right? Then this is an instantiation that we get, we proceed, then here we have chosen the first rule, okay? And now here in R1 I'm choosing the first rule, so I'm having this constraint. So we accumulate these instantiations and these constraints, and finally I get what I expected to get. That is to say that the input heap must have an object pointed to by reference X with a field F which is less than 0, and with a field G which is returned. Okay. Alright, then we consider the other path, then we will have the same basically, but now we have this other constraint, F greater or equal than 0. And then there is another path corresponding to the third test case, in which I have this null, and then I call new object, and then I generate this output heap. Okay. So, the thing is that we have been able to do this just by writing these operations in the appropriate way. Okay. Okay, I don't know if I have time for this, probably not, so I will skip it. I mean, it was just about, that aliasing can be important, and that you have to generate different combinations of aliasings if you want to achieve full branch coverage. So in this particular case, it can happen that, there is a special path that is only followed whenever those two objects are actually the same. Okay, and then again, we can do this by writing or adding an additional line to these built-ins, so that this can be done in this way. So we can get that would be the interesting test case where both references are the same, and then if I have a negative value, this set here, so we go through the both ifs in this case. Okay. Right. So that was about handling object-oriented features. Now about compositionality. So the important thing is to be able to do separate symbolic execution at the method level, and then to be able to compose the results of the different symbolic executions so that the global result is the same as doing a global symbolic execution. Okay? And this will allow scaling and handling also incomplete code and libraries, which is a very important thing in testing in general, of course. So this is the challenge. So basically, I'm doing the symbolic execution of some method M, and then here I arrive to a point where I call a method Q with this whatever arguments, and then normally what you do is that you just call it, and then the symbolic execution tree of Q will be generated for the particular constraints that I have in this point. And then what we want to do is, okay, I want to be able to do this symbolic execution alone, separately, and then instead of, when I reach to this point, I want to plug the result of this separate symbolic execution that I maybe did before, and we call this a summary for Q, and then continue and obtain an equivalent result. So this is the main challenge in doing compositional symbolic execution. So I don't have a lot of time, but just to mention that there are basically two ways of attempting this problem, which are the following. So you can either do top-down. You can start the symbolic execution at top level, and then once you arise to some point where you call a method, then you compute the summary for this method. You do the symbolic execution separately for it, but for this particular context. This is one way of doing it. So in this case, we only the required information is computed. But we cannot always reuse the summaries, because suppose that we are calling here in another path the same method TCP. It can happen that in this point you have some constraints that are not fulfilled in the other path, so you cannot reuse these results. So this is why it is called context sensitive. And then there is another approach, which is the one that we follow, in which we can always compose things. And in this case, we go bottom up. So we start from the bottom, and then we do, let us do the symbolic execution of this, then we store the summary, we do the one of this for which we use this one, and we store the summary, and so on. And then finally, when I have to do the symbolic execution of SIM, I already have this summary and this one. So I plug them, and then I can do the symbolic execution in a compositional way. And more importantly, if I have more calls, then I can reuse them, because I'm doing them without context. I don't have constraints. I do symbolic execution separately without any context. For any possible value, then you will get the summaries. The small problem is that summaries might contain more test cases than necessary. Okay. So that was about compositionality. Then now let me show you a bit this PET tool. So, some details. The core engine is implemented in Trello. Both the transformation to CLP programs and the core engine, the test data generation. And then we have a back end for an Eclipse plugin, and also we have a web interface. So this one is implemented in PHP, this one is implemented in Java. Okay. So let us just have an idea. Okay, so the command line, basically, you call the command, and then you can call pet -h, for instance, and then here you get well, some information, and then you can, there are some examples, like the one we saw at the beginning. So I can call this one. So I'm saying that I want to get test cases for this method, int exponential.intx, and then specify some options, like I want to get concrete data for the test data. I mean, I can also get only the constraints, and then I can specify the domain. So as before, I can put -10 and 10, and then I can put the verbosity level to 2 so that we get more information. And then here, I mean, this is a very textual interface. So we basically get information about the different phases, and then we get the 5 test cases. And then one has to get familiar with this to understand it. But basically, in this case, it can be understood. I mean, we just have a -10 to 0, and then the return is 1. But whenever you have objects involved, then this becomes impossible to be parsed. So in that context, this is when we need some graphical representation that I will show now. Okay, that would be the command line interface. Then also we have web interface. This is online. I mean, now I'm locally here, but it's online, so you can use it. And basically, here you have some examples. You can also upload your own example, and then you go to the package, to the class. This is the same as we saw before. So you select the method, and then you can select here the different preferences. So basically, I mean, at the end, everything is converted into a command line call. Okay, and then, okay, so let's do this, generate, and you probably have a problem now. Yes. Okay, repeat. Right. So we get 5 test cases, which is what we have. But here we get then sort of table like representation. Okay, but the interesting one is the Eclipse plugin. So let me now put it again. Right. Okay, so this is the Eclipse plugin for head. Then here I'm going to use another example, which is this is a sorted list of integers implemented as singly linked lists, ending with a null pointer. So we have a pointer to the first node, then in the node I have the integer, and a pointer to the next element. And let us consider method, for instance, method merge. Okay, so method merge basically merges this list with the L list, I mean the one of the argument, so that we get a sorted list, and so that we do not create any new node. Okay, so we just put or set the pointers between the nodes accordingly. Right. Then, so in this case, we select methods here in the outline view. So we just select merge, and also we can select insert, whatever, and then we press the button. This is the little dog bit. And now we can select different preferences. So in this case, we put this domain 1 to 10, and let us call it. Okay. And then what we get here, we get the test cases for different packages and classes organized in a tree-like structure. So here we have test cases for this package heap and for this class and for both methods. So I go through this or to see the test cases. So here we are getting 9 test cases. So observe that, for instance, this is something that probably the programmer is not expecting to get. I mean, when the input is a null pointer, then we are getting an uncaught exception. So this is one test case that can be useful. Then what more? Then, well, I also have these 2 test cases. So what is going on here? We are getting an uncaught exception. So how? Well, we can go to the test case viewer, and then we can see what is going on. So in the input, this is the input heap, I have object A, this is the list, it is pointing to a node, which is called C. And then here we have, okay, this is a list with 1 element, and list B is a list with 0 elements. First is pointing to node. So probably this is saying, okay,
I'm not considering the case where the list is empty, which is a typical error that a programmer can do, or especially students. So this is for this test case. Then another useful functionality is that we can observe the trace of instructions that each test case exercises. So, for instance, we expect to get test cases to go through the different paths. So we can either go through this if or through the else. We can either go through the while loop, enter or not. We can go through this if or this else. So, and we can see that these test cases correspond to the different combinations. So we can do the show trace, and then here you can see that this is the trace of, for which, the traces that that this test case exercises. And then in this case we can take a look at the input. So we have a list A with some node with the value 2. We have another list B with 2 nodes, one with value 1, one with value 1. And then the result, we can see the result. This is the output heap. We see that in the output heap we have the same objects that in the input heap, so we are not creating any new node. And then in the output, object A, which is the result, contains the 1, and then the 2. Okay? So this is the expected thing. So by looking at this, we can check that things are going fine. Then also we can observe the traces for the rest of the test cases. So you can see that in this case, for instance, we are not going into the loop. So one corresponds to the case where one of the lists only have one element, I guess. Okay. So I'm out of time. So I will just basically finish. Okay, so I don't have time for this, but it was just to show you that there is, this thing of trying to reach to specific program points. So basically, the idea is I want to go through a specific branch. Then what I can do is the following. So I can instrument my program so that it computes. This is already done, and we saw it. So that it returns also the trace. And then let us use this trace as an input instead of as an output. So I can provide traces, and then I can guide the symbolic execution. So for instance, if I provide this trace, then I'm forcing the symbolic execution to go through this path. Okay, in this case I'm providing a completely instantiated trace, but I can also provide partially instantiated traces, like this one, for instance. I can just say that I want to start from this, and then about the rest, I don't care. In this case, I'm guiding the tree through a specific part. Okay. So the approach that we propose to do guided test data generation is, okay, let us first have a step where we just generate traces that are promising, that are interesting, okay, that are potentially interesting. And then we can do a set of guided symbolic executions like these ones, right? And interestingly, this part now becomes much more simpler or much simpler because those are independent, so that they can even perform in parallel. So this will allow going deeper in the tree, alleviate scalability. But now the problem is in the generation of the traces. So I don't have time to go into the details. But the problem is that we get unfeasible traces unless we do it very good. So we have to try to get these properties in the trace generator. So now the difficulty is there. The generation of these traces. Okay, and one instantiation of this is to do this with resources. So I can guide symbolic execution towards paths with interesting resource consumptions, right? So that I can maybe detect a bug because there is an excessive consumption of resources. For instance, I can try to obtain the test case for the execution with the highest memory consumption, or things like that. Up to some limit, of course. And interestingly, this approach is parametric on the type of resource. And actually, you can instantiate it with number of instructions, memory, and more things. And here is where we can combine static analysis techniques with these techniques. You can use the results of resource analysis so that you can guide this trace generation towards finding interesting paths. And then you can do these guided symbolic executions and then to reach to these interesting paths. Okay, so this is the end. Well, just to mention that the important limitation in general in symbolic execution is scalability, and there are different ways of alleviating scalability. So you can, I mean, this is important. I didn't have time in my example to show it, but we can write JML specifications in Eclipse so that you can reduce a lot the number of paths. For instance, I mean, the tester might say, okay, I don't care what happens when the input argument is null. This is the precondition, so I can write these preconditions. Also, we know that now that CLPFD, I mean, the constraint solving library that we are using is a bottleneck, so we want to experiment with other constraint solving libraries. And also there is a very promising technique which is the combination of concrete and symbolic execution, which we plan also to investigate. And a further challenge is to extend this to handle concurrent programs. So we already have some results towards applying this to the model of concurrent objects. So we think it is promising, but we still have to do a lot of things. And well, that's it. So thank you for your attention.
Questions?
I think I didn't get the complete point of it. You start having a program in some language, and you end up with some test cases for that program.
Yeah.
But you cannot establish some properties that program should hold, should
Properties
contain.
in which sense? You mean
you
coverage
have
criteria?
Excuse me?
You mean the coverage criteria?
No, I think that the coverage is the only thing it's clear for me that that this method provides.
Yeah.
But
Well, I mean, that depends on the property, but I mean, memory consumption or I mean, resource consumption is preserved because you have the correspondence between names in the rules in the CLP program and instructions in the Java or in the Bytecode program. So you have this correspondence, and then you know, for instance, you know, I mean, which instructions you are reaching. You know the memory consumption or these kind of properties. You can observe them. Of course, there will be some properties that you will lose, but I don't know.
yeah, well, but for instance, imagine you start with a sorting algorithm.
Yeah.
If you want to find a test case, if that algorithm actually sorts, you cannot. I mean, what I didn't see, you can say that this algorithm, given any input, the output will be sorted.
No.
The testing is about finding
This
different
only-
outputs. I mean, you give me, for this input, I produce this result. Testing is incomplete by...
No, but I know what you mean. I mean, I think that, I mean, here we are only generating inputs. I mean, this is the important thing. And the output is the output of the program. So in principle, you don't know whether the output is correct or not. So this is the second part of a unit test. So here we are only focusing on generating test data. Then after this, you will have to have some specification, a post condition, and then you will have to check that the post condition is being guaranteed or satisfied by the result. But this is not what we are doing here. I mean, this requires integrating this with a specification language. Okay. But here we are generating test data. So you run the program, and then we are just guaranteeing that with this test data, you are covering all the paths up to a certain level. Okay. Then checking that the results are the ones that you expect. This is something that, I mean, the tester will have to write the specification. So this is something you cannot avoid.
Okay,
This answers your question?
Yeah, of course.
Okay.
Yeah.
Miky, I think that in all the examples, the result, the set of test cases that you obtain are concrete cases. So you don't give as results cases in which some of the variables appear as constraint. This is particular of the example. This is intended because you do some labeling.
Exactly. This is intended. I mean, in principle, you get just the constraints associated with each path. You can actually, I mean, there is a parameter there where you can say whether you want to get concrete data or the constraints. So if you want to get the constraints, you can get them. And then we are doing labeling at the end. so that we solve the constraints and then we show to the tester only one particular one.
So I think that in some cases, doing a labeling phase maybe may not be very good in the sense. Imagine an extremely simple example. Your program simply returns 1. And then for any input, your program is going to return 1. And maybe because of your labeling, you say, my input is 0 and I return 1. And maybe this is a good case, but maybe the function you should...
You're absolutely right. I mean, that depends on what are you trying to do, I think. So if you want to do testing and automatically doing JUnits that you want to run, then you need to solve the constraints and you get particular values. But if you are doing like program comprehension, I mean, you want to know what is going on there, then it is sometimes much more useful to observe the constraints, really, like in this example. Then you see when n is less than 0, then the output is greater than 5. I mean, sometimes this is